Welcome, GeoTrig. This is section 2-1, Patterns and Inductive Reasoning. The essential question is, what does it take to prove something is false? And let's begin. So this whole section it's just about learning how to do proofs and getting ready for the future section. So it's really just a lot of preparation, but it's kind of fun. So inductive reasoning, this is our first vocabulary word. Inductive reasoning is reasoning based off patterns. So you find the pattern and you figure out, well, what are the next steps of the pattern going to be? So it's looking at part of a pattern, just being able to reason what's going beyond. So let's take this first example. What are the next two terms? 2, 4, 6, 8. So you're looking at those numbers going, okay, we're multiplying by 2 every time, times 2 times 2. So that's the pattern. So my next two on the patterns are going to be 16 times 2 is 32, and 32. And the next one's going to be 64. So those are the next two terms. Now let's look at these shapes. So it doesn't have to be numbers. It could be, not shapes, figures. So looking at this first figure, and the next figure, so it looks like they're all circles with a different shape inside. So a triangle, and then it goes to a square and a pentagon. And wait a minute, this is 3 sides, this is 4 sides, this is 5. So I'm guessing my next shape is going to be a circle. So I'm going to draw a perfect circle, just like this, and with a 6-sided pentagon or hexagon in the middle. So I'm going to use something to cheat because that's more fun. No. And if you draw a hexagon, just 3, 3, 4, 5, and 6. There's a perfect hexagon. So that's the next one in the figure. Now, let's do something a little bit more relevant to you. Look at this. What are the next two names on this list? So Sauron, Isildur, Deagle, Smeagol. Who are the next two? And you're going to look at that and go, oh yeah, of course, these are the Ringbearers, because Sauron had the one ring to rule them all. Then it passed on to Isildur when he defeated Sauron, and then it landed in the lake, and Deagle got it, and Smeagol wanted it because it was his birthday. And then the next two Ringbearers were Bilbo Baggins, because he went on an adventure, and he found it in Gollum's cave. And after Bilbo got it, Frodo got it, because Bilbo was old and he couldn't go take it to Mount Doom and destroy it. Now, for extra credit, tell me the rest of the Ringbearers all the way to the ring was destroyed. Post it on the YouTube channel. Extra credit. Conjectures. Unproven propositions that appear correct. So this means I might say something and I think it's correct, but we don't have any proof that it's correct. It's just, it looks like it's correct based off the pattern. So looks correct. Looks correct. Based on pattern. So what does that mean? Well, someone might come up with a conjecture, but we can come up with counterexamples that show a conjecture is incorrect. Because they're not proven, it's just something that we think is right. So let's take some examples. What is a counterexample for each conjecture? I'm going to conject that if the name of a month starts with J, it is a summer month. I might say that. Say, well, yeah, they do, because June and July, those are summer months, close enough. And then you say, but wait, what about January? Because January is clearly a winter month. So the counterexample is January, because that's a J month and it's definitely winter. Another example, you can connect any 3 points to form a triangle. So I'm going to say that because I could just draw any 3 random points, boom, boom, and boom, and say, oh yeah, you can draw perfectly straight lines to form a triangle. And they always work, right? See, these points always work. But wait, what's a counterexample? What if all 3 points were in a straight line? Just like this. Then you can't form a triangle because there's a perfectly straight line that goes through all of those. And it's perfectly straight going through all these points, and it does not form a triangle, it just forms a line. So there is my counterexample, 3 points in a line. So I could write my counterexample is 3 points in a line. All right, let's move on. Another counterexample, when you multiply a number by 2, the product is greater than the original number. So multiplying some number by 2, so I'm going to go like a times 2. And the product multiplies to something greater than the original. Well, yeah, because if you double anything, you get something bigger, right? In that first example, 8 times 2, 16. Like every time we doubled, we got something bigger, so that must be true, right? But wait, a number could be negative. So a counterexample could be, what if I did negative 8 times 2? That comes out to negative 16. Negative 16 is not greater. So you could say your counterexample is multiply by a negative. Or you could multiply by 0, because 0 is not greater than 0. So multiply by negative, multiply 0. These are all great counterexamples. Let's try this out. So look at this and pause. 3, 2. So find one counterexample to show the conjecture false. Angle 1 and angle 2 are supplementary. So one of the angles is acute. So what's supplementary angles again? These are angles that add up to 180 degrees. Hope you know that. Just if you don't, make sure you just check it. So one of the angles has to be acute, because that's right, because if you draw two angles are supplementary, and if we did a line, oh, not like that, come on, I don't like this thing. If I draw a flat line like this, well yeah, because you're going to have another line coming out of it, an angle like this, and one's got to be acute, right? Like this angle's acute, and this one's obtuse, because one's always got to be smaller just to make that happen. But wait, that's not true. Because you got to think, what case is that not true? And that's right, true in one case, when both angles are 90 degrees. Because two 90-degree angles add up to 180 degrees. But they are not acute, because acute is less than 90 degrees. So this is the case, and you could say your counterexample is two 90-degree angles. They are supplementary, but they are not acute. Another example. Pause the video. All right, so one counterexample, so the conjecture is false. All four-sided figures are squares. Whoa. Well, that doesn't have to be true at all, because it just says four-sided. So four sides means a figure, so it has to be closed, but there's four sides. I can just do four random sides. There's one, there's two, there's three, and there's four. That's definitely not a square, but it's four-sided. And we could do other shapes too. We could do a rectangle, because a rectangle is definitely not a square, but that's close to a rectangle. We could do a rhombus where they're all even sides, but they're just slanted. You could do parallelograms, which is the slanted rhombus. You could do a trapezoid. There's tons of examples of a four-sided figure that is not a square. So there you go. Next one, find a counterexample. Pause the video. All right, so find one counterexample. If triangle ABC is a right triangle, triangle ABC is a right triangle, so angle A measures 90 degrees. Now, well, that doesn't have to be true at all. So let's draw a triangle that's right. So I'm going to draw a perfectly right triangle. Okay, so there we go. And so that means this angle will be right, and then we have two other angles. I don't know what they are, but they could be two different angles. Now, angle A measures 90 degrees. Well, this angle measures 90 degrees, but with a triangle, when I label it ABC, it doesn't say which angle is A and B and C. This could be A, and that would be 90 degrees. What if this was A, and this was B, and this is C? So you don't, just because it's triangle ABC doesn't mean that the right angle is A. So there's an example right here. Could be B or C for that right angle. And that's it.